If your top results all say the same thing, relevance is not enough. I'll use Maximal Marginal Relevance with embeddings in Python to make search results more diverse and useful. This is the workflow you'll know how to run when we're done, which ranks texts for relevance, penalizes duplicates, and returns diverse top results. I'm Professor Pi, teaching AI foundations with simple Python. Search systems often return results that are individually relevant, but collectively repetitive. Imagine a user asking how to install Python on a Mac and getting 5 answers that all explain the same step. That feels like wasted screen space and a missed opportunity to cover different approaches. Maximal Marginal Relevance, or MMR, solves this by balancing relevance to the query with novelty across the chosen set. At a high level, MMR rewards documents that are close to the query and penalizes those that are similar to what you've already picked. Think of it as a committee choosing speakers. You want the best experts, but you also want different perspectives. The strength of MMR is that it is simple and model agnostic. It works with any embedding or similarity score and scales from tiny demos to thousands of documents. We will build a tiny experiment. It will embed a small corpus, show a naive top 3 search, then apply MMR to pick a more diverse top 3. You will see a numeric redundancy score and a simple topical bucket count. That keeps the idea concrete before we look under the hood. Next, we will embed the tiny corpus and run a naive top K search. This snippet uses sentence transformers to embed a tiny corpus and run a naive top K cosine search. The list docs holds short snippets, and Q is a simple query about installing Python on a Mac. The sentence transformer object loads the all-mini LM L6 v2 model, and in code turns both docs and the query into L2 normalized embeddings. A dot product between doc vectors and the query vector gives cosine similarity, and arcsort selects the top 3 hits. To quantify redundancy among those hits, the code averages their off-diagonal pairwise similarities. A high average means near duplicates are crowding the top ranks. The printed average pair similarity indicates how repetitive the naive top K results are. Next, we will apply MMR to those embeddings to encourage variety. This example applies maximal marginal relevance to reduce duplication in the retrieved set. The function MMR scores candidates by a weighted mix of relevance to the query, the array rel, and dissimilarity to already selected items, the div term. On the first iteration, it picks the most relevant item. Afterward, it downweights items similar to the chosen set, encouraging diversity. The inputs X and Q are the sentence transformers embeddings from the prior step, and K is the desired set size. The lam parameter trades relevance for diversity. Higher values lean toward relevance, lower values increase spread. The printed average pair similarity should drop versus naive, showing fewer near duplicates. Next, we will label the selected documents into simple topical buckets to measure coverage. This code turns the abstract diversity signal into something concrete by bucketing results into simple topics. The helper function topic assigns each document a label based on keywords like Mac plus Python, then, or PyTorch. Using the MMR selected indices IDX from the previous step, the set comprehension gathers topic labels for the chosen documents. Taking the size of that set gives the number of distinct topical buckets represented in the final selection. You can adjust the keyword rules in topic to match your domain more closely. A higher unique topic count means your top results cover more ground, which is exactly what diversified retrieval aims to achieve. Next, we will sweep the lambda parameter to see the relevance versus diversity trade-off. This snippet sweeps the MMR lambda parameter to show its practical impact on redundancy. For each lambda value, it reselects 3 results and computes the average off-diagonal pairwise similarity among them. Lower lambda increases the penalty for picking items similar to what is already selected, while higher lambda favors raw query relevance. Because the sentence transformer's embeddings are normalized, the pairwise average gives a clean, interpretable proxy for duplication. If your domain needs tighter topical spread, lower lambda is helpful. If you must keep top hits very on topic, push lambda upward. The printed pairwise similarities make the trade-off visible in numbers. Next, we will compare a simple baseline ranking to an MMR refined ranking and compute a diversity gain. This example assembles a compact baseline that retrieves and then diversifies. It first ranks documents by cosine similarity to the query and grabs the top 4 candidates. The same pool is passed through MMR with lambda set to 0.6 to produce a diversified top 4. Using the normalized sentence transformers embeddings, the code computes average off-diagonal pairwise similarity for both sets and takes the difference as a simple diversity gain. You can lift K to fill more slots and still keep results varied. A positive diversity gain means MMR reduced redundancy in the visible results while keeping them relevant. In a production setup, you would replace the tiny list with a real index. The same flow maps cleanly. Embed your documents, fetch nearest candidates with an ANN index, then re-rank those with MMR. The metric and bucket checks we used scale as quick diagnostics during development. Recap: Maximal Marginal Relevance blends relevance and novelty to reduce repeated answers. Use it when your top results are useful but too repetitive, like FAQs or multi-perspective search. Caveat: tuning the lambda trade-off is essential because too much diversity can lower immediate relevance. Next step: tune the MMR lambda on your corpus and measure diversity gain versus hit rate to find the right balance. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.